Hi everyone! So in this video, we're going to go ahead and discuss something called scientific notation. So let's go ahead and get started. Okay, so scientific notation is helpful because it lets us write really large or really small numbers easily. And in chemistry, we're often dealing with either really large or really small numbers. This is because atoms are so small, but when we have their measurements, we're often dealing with a large number of them. So scientific notation kind of becomes our best friend in chemistry. Okay, so scientific notation consists of two parts. The first part is a number between 1 and 10. So 1 all the way up to anything a little bit less than 10. And then the second part is we are multiplying that number by 10 raised to some power. Now, if we're raising it to a positive power, then that means that we have a large number, or really anything greater than 1. If we are raising 10 to a negative power, that means that we have a decimal, so a small number. Okay, so to give you an example of this number written out in standard notation is 6.02 sectillion, which is the mole that we'll be using a bunch this year. And as we look at that, it is a pain to deal with. There are so many zeros, it's hard to know where we are. It's just really unwieldy. But if I write it in scientific notation, it becomes 6.02 times 10 to the 23rd, which, although might seem a little foreign, is actually a whole lot easier to deal with. So let's go ahead and work through some examples of how to do scientific notation. Okay, so let's go ahead and try out some examples using scientific notation. So the first one in your notes says the sun has a diameter of 1,392,000 kilometers. And we want to go ahead and put this into scientific notation. So the first thing we need to do is figure out where the decimal point is going to go. Because remember, we need a number between 1 and 10. Well, I can go ahead and actually replace this comma with my decimal point. Because if I do that, I'm going to have 1.392. And that is between the numbers 1 and 10. So that's where I'm going to put my decimal point. And I can go ahead and start to write out that beginning. So 1.392. And we're going to multiply that by 10. Okay, so then the next thing is we need to figure out how many times we move the decimal point. So originally it is here at the end, kind of an invisible decimal point. And we're going to count how many times we need to move it over in order to get between the 1 and the 3. So I like to kind of do little loops to kind of count. So 1, 2, 3, 4, 5, 6 times to get it over between the 1 and the 3. So it's going to be times 10 to the 6th. Now, if I think about this is a big number. It's bigger than 1. So because it's a big number, I need a positive exponent. And then the final thing I need for this is simply my unit. So remember, no naked numbers. We always want to have units on them, keep them decent for public. This isn't math class where you can do scandalous things like have numbers without units. Okay, so 1.392 times 10 to the 6 kilometers. Now, one thing I do want to point out is sig figs when it comes to scientific notation. So if we look at this number, the zeros did not count because they were trailing zeros and we didn't have a decimal point given to us. So we had 4 sig figs. Well, if we look here, this also has 4 sig figs, so it works out. Okay, so let's go ahead and try the next example. The typical atom has a nucleus with a diameter of 1.6 times 10 to the negative 15 meters. So as I look at that number, I'm thinking to myself, wow, that's going to be a really little number because I have a negative exponent, which does make sense because we know atoms are really small. This is measuring in meters, so it's going to be a really, really small number. So how I like to do this is kind of work in reverse now. So I'm going to start by writing out my 1.6. And since I know it's a small number, I'm going to have 1.6 at the end and I'm put zeros in front. So I'm going to write my 1.6 kind of off to the right so I have plenty of room for all the zeros I will need to add. And then right now I have the decimal point here between the 1 and the 6, and I'm going to move it 15 times to the left. Now notice, this is the number of times I'm moving my decimal point. This is not necessarily the number of times I'm adding a 0. Okay, so I'm just going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times. That's a lot of little loops. Okay, so let's go ahead and fill it in with zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so notice I have 14 zeros in front, not the 15. That's why we count the number of loops. Okay, so if I were to rewrite this so it looks nice and pretty, some things that I like to do, I like to put a 0 in front of the decimal point just because I think it kind of helps to draw my attention that there is something there. Also, I like to group my zeros into sets of 3 just because it makes it easier for the eye to look at it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then the 1, 6. Okay. And then the final thing that I am missing is my unit. So I would just go ahead and add meters. Now, do you need to group your zeros? No. If you don't, that is perfectly okay. You will still get the right answer. I just think it makes it a little bit easier to kind of count these, which makes my life easier as I'm grading. Okay, so let's go ahead and move on to the next example. So the speed of light is 3.0 times 10 to the 8th meters per second. So if we think back to our prior experience, hopefully you know that the speed of light is really, really fast. So makes sense that it's a big number, which is why we have a positive exponent. So I'm going to start by writing my 3.0. And since it's a big number, I know I'm going to add zeros afterwards. And again, we're going to count the number of times that we move our decimal point. So we're going to move it 8 times to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And again, I'm going to go ahead and fill that in with my zeros. So 1, 2, 3, 4, 5, 6, 7. Okay. So again, the power of the exponent does not correspond to how many zeros we add. So be careful with that. So if I were to rewrite this so it looks nice, neat, and pretty, remember we need to use commas between the zeros for those big numbers. So we have 300 million meters per second. Okay, so that's the next one. So example 4, the mass of a proton is, okay, that is a ton of zeros. And if I think about this, I expect it should be a really small number because we're talking about protons, which are teeny, teeny, tiny. I can't see them. So they're going to have a really small mass, which means I'm going to have my exponent, my times 10, raised to a negative power. So let's first think about where we want to put the decimal, because we need that number in front to always be between 1 and 10. So I'm going to go ahead and end up putting my decimal point right there between my 1 and my 6. So that gives me 1.67. So if I go ahead and write that out, 1.67, and I know it's going to be times 10 raised to some negative power. And I know it's negative because I have a small number. Okay. Now, if I go ahead and count my zeros, well, let me rephrase, not my zeros, but the number of times I move my decimal point. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So negative 27, and then again, don't forget your unit for kilograms. So again, just a reminder, whenever I have a really small number, so anything that's a decimal, I need a negative exponent. If I had an actual negative number, then I would have the negative sign out here, but I don't. I have a positive, which makes sense for the mass of a proton. Okay, so thanks for watching, everyone. I hope that this helps explain the concept. So make sure you're getting some practice in, and if you have any questions, please let me know. Otherwise, have a great day. Bye.